Okay. We have introduced simply connected domain concept last Tuesday. So now we will state theorem 14.2.1. Okay, the Cauchy's integral theorem in a simply connected domain. All right. So now D here is a simply connected domain, and P a point in D, okay. And F a complex function which is continuous on the domain D, and it's in D minus P, okay, which means that the function f is analytic on D minus the set of P, okay. Well, with this condition, then if we compute the line integral, sorry, of the complex function f over a simple cross path of gamma, then this value will be 0 for every simple closed path, okay, gamma in D. So this integral, this equation, or this identity is true for every simple closed path gamma here. Okay. But the domain can be any simply connected domain. If we compare this theorem with the previous theorem, which is the Cauchy's integral theorem in a convex open subset, we know that here a convex open subset is a simply connected domain. Okay. So convex open subset is a special type of simply connected domain. And so the Cauchy's integral theorem in a convex open subset that the gamma here can be any a coarse path, not necessarily simple. Okay, so if D is a convex open subset, which is a very special type of simply connected domain, then this identity is true for every closed path, not necessarily simple. But if we extend the theorem from convex open subset to simply connected domain, okay, so simply connected domain is wider, all right? Then then this identity is true only for simply closed paths. Okay, so you have to distinguish the difference between these two versions of Cauchy's integral theorem. Okay. Any questions? Okay. Right. So after we introduce or we state several versions of Cauchy's integral theorem, then we will now consider Cauchy's integral formula. Alright, suppose gamma is a closed path. And omega is the complement okay. So gamma is a closed path in the complex plane, and omega is the complement of gamma star in C. Okay. Now, since gamma is a closed is a closed subset of C, now omega is an open subset of C. Okay? Right, so we know omega is the is an open subset of C. Okay. Now define a complex function okay. We call IND sub gamma of Z okay, to be 1 over 2 pi I of the line integral over the path, the closed path gamma, and the integrand will be eta minus Z d eta okay, for all Z in omega. Z should be in the complement of gamma star. Why? Because if Z is on gamma star, then if we integrate over the closed path gamma, then a point and eta may equal to Z, okay? And so this is undefined, okay? But if Z is in the complement of gamma star, so here, say, okay, so this is gamma star here. And for a point, say here, Z here. So Z should be in the complement of gamma star. Okay. Otherwise, if Z is on gamma star, then as eta trace over the the path, then there is an eta which is equal to z. Okay, and the denominator becomes to be 0, which is undefined. Okay, so that. Okay, so this function, this is a complex function, is defined on omega. Okay, and this function, which is called the index of points z in omega with respect to the cross curve up the cross path, gamma. Okay. Okay, so this is the index function we have. Now we show that the index function is continuous on omega. Okay, so we want to show that it's continuous. All right, so we fix a point g sub 0 in the omega here. Now, since gamma t minus z0, right? So gamma t minus z0 is a continuous function because gamma t as a path is a curve, and as a curve it is a continuous function. Okay. So this is continuous function minus a constant. So again, this is a continuous function. And then if we take the absolute value, then this is also a continuous function. On the parameter interval. Alpha to beta. Okay. And this, we know the parameter interval, which is closed and bounded. Okay. All right, and because Z0 is not in gamma star, because Z0 is in omega, omega is in the complement of gamma star, so Z0 is not in the range of the path. Okay, so there is d greater than 0 such that gamma t minus z0 greater than or equal to d for all t in alpha beta by the extreme value theorem. Okay, so by extreme value theorem there. Because this is a real value function, right? A real value continuous function on a interval which is bounded and closed, right? And by the extreme value theorem, the function, the range has maximum value and the minimum value, okay? But the minimum value should be greater than 0, okay? So that we have a lower bound, which d is greater than 0. Okay, because F's value always greater than or equal to 0. But never 0, why? Why? Because that Z0 is not in the range of the path, so the difference never 0. So the absolute value always positive. Okay, and we have the minimum value, so this minimum value should be positive. Okay, right. So this is from the extreme value theorem we have in calculus. Okay. Any questions? All right. Now, since omega is open, okay, so there is a neighborhood all right, a neighborhood of Z0 contained in omega. Okay. Now, since gamma t minus t 0 is less than equal to gamma t minus z plus z minus z0. Okay. For all z in C, this is just the triangular inequality. Okay, in the complex plane. So we have okay, that gamma t minus z would be greater than equal to gamma t minus z0 okay, minus z minus z0. Okay. Okay, and if we select z, so the lower bound is d, and we select the z which is not far away from z0. Okay, so for example, if we select z, which has distance, okay, from z0 less than d minus 2. Okay, so we have the lower bound. So this is d over 2 for all t in alpha, beta. For any z such that z minus z0, okay, is less than the minimum of the 2 and the rho. Okay, so now I will say that a rho neighborhood. A rho neighborhood, okay, I use a rho neighborhood. It's something that is the set of z such that less than rho. Okay, so rho neighborhood, okay, is that, so this is z0 rho. Okay, so this is a rho neighborhood of z0. Okay. Okay, so this is this zone neighborhood must contain in omega. Okay, and so we select the z such that the distance between z and z0 will be less than. So the z should be in the zone neighborhood, and also also the distance is less than d over 2. Okay. Okay, so the minimum, we know that the minimum would be upper bounded by d over 2. So if we do the subtraction, we have lower bound here. Okay. So you see for any z, has distance from z0 less than the minimum of d over 2 and the rho, we have the magnitude of the distance between gamma t and z has a lower bound d over 2 for every t in the parameter interval. Okay. All right. So now we have the index gamma of z minus the index gamma of z0. All right. So now we estimate the difference between the index of z and the z0. Okay. Okay. And by the definition, we know this is gamma 1 over eta dz minus gamma 1 over 2 pi I 1 over 2 pi I gamma eta minus z0 d eta is psi. I'm sorry, it's not eta. But d psi, okay, is psi here, absolute value. So this is 1 over 2 pi here, and gamma psi minus z minus 1 over psi minus z0. Okay, and the d psi here. Now the difference comes to be and z minus z0. Okay, so that z and z0, because they are in this line integral, the z and z0 are constant. Okay, so we will have here 2 pi. Okay, and now alpha to beta. Okay, now we have z minus z0 and gamma t minus z times gamma t minus z0 as value, and gamma prime t and the dt. Okay, so we have the upper bound here. Okay, and so we have z minus z0, and this is 2 pi. Okay, and the alpha beta. And 1 over gamma t minus z, and the gamma t minus z0 here, gamma prime t, and dt. Okay. Now, so if we select all the z which is less than the minima, then we know that the magnitude of the difference is low bound d over 2. But the magnitude here, gamma t and z0, has low bound d. So that we have upper bound, okay, and z minus z0 and 2 pi, and times 1 over d times d over 2. Okay? So that the d over 2 here, so this is the upper bound, because the lower bound for this one is d, and the lower bound for this difference is d over 2. Okay, and we take the inverse, so this has become the upper bound. All right, and the alpha beta, gamma prime t, and dt. But this is the length of the curve path. Okay? Okay, so that the upper bound becomes to z, down to here, comes to L d square pi, and times z minus z0. Okay. All right. So now, if the z is very close to z0, then the function value is index of z is very close to index of z0. Okay, we start. Okay. All right. So as z goes to z0, we have the index gamma of z will goes to index of gamma of z0. Okay. So that the index function is continuous at z0. Okay. Any questions? Right. So for any fixed point in the complement of gamma star, we find that the index function is continuous. Okay. All right, and the z0 is any point we select in omega. So the conclusion is that that's the index function is continuous on omega. Okay. Any questions? Now we state a theorem about the index. Okay. This theorem is called the winding number index of a point with respect to a closed path. Right, so once again, gamma is a closed path in the complex plane. Omega is the complement of gamma star in C. So once again, gamma is an open set. Okay. Then the index function. Okay. The index function IND gamma of Z is an integer valued function on omega, which is constant in each connected component of omega, and which is 0 in the unbounded component. All right. So suppose we have suppose like this is gamma star here, and the complement is omega here. Now the connected component is that the subset which a connected subset. So the component, the connect component, all right. So the unbounded component will be this one. Okay, so we have, so this is unbounded connected component. Alright, so connected component is that the biggest connected subset. Alright, the maximum or the maximum connected subset. So this one is also a connected component. Alright? So let me draw the picture. And this one. Right? So the blue, the whole blue region is a maximal connected subset. So it's a connected component. Right? we have this one is also a maximal connected subset. So it's a connected component. And the last one, the yellow one, okay. So how many connected component gamma have in this case? Right? Unbounded. There's one unbounded connected component, right? And 1, 2, 3, 4. And the 4 bounded connected component. So there are 5 connected component in this case. Okay. So connected component okay. So connected, I will see here, connected of a set A and C is a maximal connected subset of A. Okay? So that to identify a connected component of a set in the complex plane, well, you will find a maximal connected subset. Okay, connected subset. Maximal means that you cannot extend this subset furthermore, right? Without violate the connectivity, okay, and connectedness. So from here you can see that the omega here, the complement of the curve of the gamma star, right, we find there are 5 connected components. And of course, one of them is unbounded. So there is one and only one unbounded connected component. And we have 4 bounded connected components here. Okay, as indicated by different color here. Okay. Now, the theorem tells us that the index function, all right, because we know the index function is defined on omega. Okay, so every point on omega has an index, right, with respect to the closed path gamma. And the theorem says that the index function is an integer value function. So the value can be only integers. Okay? And it is constant in each connected component. The reason is because the index function is continuous. So, and because it's integer valued, right? So that in the green region, in the green component here, the value of the index. So every point in the green connected component has the same integer value. In the blue connected component, all the points in the blue connected component has the same index value. Okay, right. And similarly, for all the points in the red connected component, the index, they have the same index value. Okay, so in each connected component, the index function is constant. Okay, For the unbounded kinetic component, the index value should be 0. Okay, so we know the index should be 0 there. Any questions? And the index of a point with respect to a cross path sometimes called the winding number. So the winding number is that so the point, if we do a lot of, okay, so because that for a point, see here, if we select a point, say a point here, P. Okay. Now the path will, okay, maybe it's not very clear. Okay, we pick a point here, P here, in this kinetic component. Now the path will, for example, the path will go, for example, like this way. Okay, it's go. So you will wind, right? Around the point. Okay, you are around the point. So you're winding. And the effect winding, because in this winding there is no effect on this point. Okay. So the winding number, in particular, if there is a point and if we do something like that, right? So you can see, suppose we start here, okay? So it's 1 circle, 2 circle, 3 circle. So you can say, in effect, the path will winding, right, the point P here for 3 round, you can say. So the winding number would be 3. Okay, now let us see. Starting from here, 1, 2, 3. Okay, so the winding number will be 3 in this case. Okay, so for this point. But if we have a point here, now starting here, there's no effect, right? No winding. But start here, 1 and 2. So the winding number would be 2. Okay. For this point, so it's P1. Maybe I will say this P3, P2, P1. For P1, there's no effect. There's no winding about P1. But the last round, you have winding. So the winding number will be 1. Okay. But the point P0 here, if you trace out, there is no winding over P0. So the winding number is 0 for P0. Okay. Right. So this is the meaning of winding number. Okay. Right. So sometimes people call the index as the winding number. Okay, because that you can trace, you can see the effective rounding. So 1 round means that you go around 660 degree, 2 pi, right? 360 degree as a one, okay? A round there. Okay. Okay. Right, so this is some particular path you can have, right? For this case, right? So the one number will be 3 and 2 and 1 and 0. Okay. For this specific case. Okay. So this confirmed to the theorem because that the point here is in the unbounded kinetic component. And the index or the one number of a point P in the unbounded kinetic component should be 0. Okay? As stated in the theorem here. Okay, it's 0. And the component, and so even though we know that the index function is integer valued and is constant in each kinetic component. So we know in this kinetic component in here is constant, the index constant. In here the index is constant too. And in here this is constant. Okay, and here the unbounded kinetic component. Okay. Okay. So the one number is 0, 1, 2, 3. Okay. Now, so it's easy to see here. Now, how about here? How about here? Well, 1, 2. So you can see the one number here should be 2. But the one number may be oh, by the way, okay, so it's clockwise. I'm sorry. So the one number is -3, -2, and -1. I'm sorry. Because that there are direction, right? So we usually name that if we winding a point counterclockwise, okay? It's positive because counterclockwise direction is usually assigned to be positive oriented. But in this way, we want it's clockwise. 3 times. So this is -3. I'm sorry. This is -3. This is -2 and -1, and there's 0. Okay. And for this one, because this way is clockwise, so we know we go there, here, and then again. So this is -2. So this is a -2 here. Okay. And a point here, what is the one number? There is no effect. So the go, no effect. So this is -1. Okay. How about a point here, P? It go, this is what? You see here, go there. And so this is +1. Okay, so that once, okay, so from here, nothing, right? So this should be +1. Okay. Right. So that there are ways you can go around them. How about the yellow part? P. So what is the one number? Well, we go this way, and we have nothing to do with the point. So this is +1 again. Okay. Very interesting, right? So +1, +1, -1, -2, and the 0 here. This is 0, as we see. So, so now the next we will provide a technical theorem, which is much more easier for us to identify the Y number in a kinetic component. Okay, so let's see here theorem. So right. So gamma is a closed path. Okay. In C with parameter interval alpha to beta. Suppose we have U and V in between alpha and beta, and A, B are complex numbers okay, and the absolute value of B is gamma. All right, of course B has positive magnitude, and 1 gamma U equal to A minus B, and the gamma B equal to A plus B. Okay, second, gamma of S minus A less than R if and only if U S is in between here, and third, gamma of S minus A equal to R if and only if X equal to U or S equal to V. Okay. So now, so we will see here, there is a part, okay, and go this way, right? And the point here, so this is gamma of U, and this is gamma of V, okay? Because U goes to V, so the direction or orientation is from gamma U to gamma V, okay? The orientation is here. And we want to select, okay, an A, right? So that at the 2 points, gamma U and gamma V, all right, the distance is equal to A. So we will connect them. So you can see, you can select here and find the middle point. Okay, find the middle point here. So you can see here. All right, so this is A. Okay, so suppose we find A here, and the distance. So this is R. Okay, so the distance This is R. This is R. Right? And so we draw a disk. All right, so this is a disk, okay? And so this is R. Okay, we have, so the radius, so you have a disk with radius R. Okay, you have radius R here. And you can see for all the S in between U and V, so all the S in between U and V is there. So this is the gamma S here. So gamma S minus A here, you can see that the distance is less than R, the radius. Okay, so you see the radius here. Okay, so this is the situation. Okay, and all right, and A plus B, so the B would be this number. Okay, so the distance, and here is minus B. So as you can see, a complex number can be regarded as a vector, right? A two-dimensional vector. So that this is the distance. So you can see that in here, the B is equal to gamma V minus A here. Okay, and you know that gamma U minus A is equal to minus B here. Okay, so you can determine A and B. Okay, so A is just the difference between this complex number and A. Okay, gamma V and A there. Okay, so the situation 1, 2, and 3, everything is just like this picture. Okay, just like this picture. Okay. So the picture I draw here is equivalent to the verbal description here. Okay, and the disk. So this is the disk with the center A and radius R. Okay, so this is the disk. Okay, this is the disk. Now, the disk has been partitioned by this path into two domains, right? So, into the domain, and we will indicate that A plus BI. So B is the vector, right? Is this vector, okay? And if we add 90 degrees, so we go there this way. So here is D plus. Okay, so here will be D plus. And this part will be D minus. Okay, so we will say that assuming that Furthermore, the disk, okay, with center A and radius R, so this disk, and minus gamma star, right? So minus gamma star is the union of two domains, D plus and D minus. Okay, so we have two domains. Okay, I use this part. So this is D plus, okay, and this is D minus. So here this is D minus. And how do we identify D plus and D minus? Okay, labeled. So we label this. So that A plus BI, okay, is in the closure of D plus. Closure of D plus means that we include the boundary. And so this point, you know, this point here is A plus BI. Why? Because if a complex number multiplied by I, the angle will increase 90 degrees, right? So it will go up, go to here. Okay, because this is A plus, because this is A plus B. Okay, A plus B. But if B, so B is this vector. But if B multiplies I means 90 degree increase, right? You rotate the B by 90 degrees, so it will go here. So this point will be A plus BI. Okay, the opposite side will be here. So this point, okay, and this point, this is A minus BI. Okay. So minus I is that if you rotate minus 90 degree, okay, minus 90 degree, so you get is this point. So this point should be in D minus, and this point should be in D plus. Okay, so that this is in D, and A minus BI is in D bar minus. Okay, so that's why we know this is D plus, this is D minus. Okay. Okay, so if we go, you can see, if we go from this point to this point, the orientation here, then D minus will be on the right hand side, and D plus will be on the left hand side, right? If you go this way, right? So if a person walk from gamma, from this point to that point, in this direction, right? If a person, then D minus will be on the right hand side, and D plus will be on the left hand side. Okay, so another description is that so I can say as gamma T traverse, all right, as gamma T traverses the disk, okay, from gamma U, which is A minus B, to gamma V, which is A plus B, Then D minus is on the right. Okay, and D plus, okay, is on the left of the path. Alright? Alright, so this is just the picture. Alright, so all the verbal description can be seen from this picture. Okay, so if you understand the picture, you will understand all these descriptions. Any questions? Yes. Open disk. In the cordial. The cordial means that the open set with the boundaries. Yeah. If you have no problem with the diagram here, then I will write down the conclusion. Is that okay? Alright, so if this is okay, then I will state the conclusion. Then index gamma of z is equal to 1 plus index gamma of w. Right? If z is in d plus, okay, and w is in d minus. So the index, you know, d minus is on the right, right, and d plus is on the left. And the point on the left has index 1 more than the index of the point on the right. Okay. Is that okay? This is the conclusion. So now we will look at, so if I erase here, we know the unbounded kinetic component has index 0. So we start from here. And we select this part. Okay? So we select this part. So here, so we select point. Okay? And the way is, let me see the direction. It's very important. Here, okay, this way. Alright, so this way. We go this way. Now, so here, this is gamma u. This is gamma v. Right? Remember, alpha, u first and v second and beta. So we travel. Okay, the orientation must be from gamma u to gamma v, this way. Okay. Okay, and so the right, so this is in here. The right is d minus, right? And the left is d plus. Is it okay? Is that okay? Just like here, we this direction, but we are going this way, and so that the core here, this is A, and you construct okay. So this is A plus B. This is A minus B. Okay. And go this way. So the point here is A plus BI. The point here is A minus BI here. So this is D minus. This is D plus. And the index of the point in D plus is one more the point in D minus. But in D plus, the index is 0. So in D minus, the index must be minus 1. Okay? Now, to determine the index in this region, in the yellow region, okay, so now we select an arc. So we see this way, all right? So this time we select these 2 points, okay, and the direction will be here. Now, so we go this way, right? The right-hand side here is D minus, and the left-hand side is D plus here. So D plus is minus 1. So minus 1 is one more than the index point in D minus. So that the index, it would be minus 2. Okay, and finally, for here, we select the point here, 2 points. Right, and we work from gamma U to gamma B, right? So the right, this gives us D minus, and this is D plus. And so this is minus 2, so this is 1 less than minus 2, which must be minus 3. Okay. So by the theorem, you know the YE number in each kinetic component. Okay. How about this one? We go back here. Okay. Now the unbounded kinetic component has index 0. How about the index of the blue kinetic component? Well, so we select here 2 points. So this is gamma U, this is gamma V. Okay, and we travel. All right, and so the right-hand side will be D minus, and the left-hand side will be D plus. Okay? Now, the D plus has index 0, so D minus should has index minus 1. Okay. All right, how about the orange region? Well, we will select 2 points. So this is gamma U and gamma V here. Now, the right-hand side is D minus. The left-hand side is D plus. Okay, so D plus is minus 1. So D minus should be minus 2. How about the red one? For the red one, we select the 2 points here. So this is gamma U, gamma V. And this way, so this is D minus, and here D plus. And D minus is 0, so D plus is 1. Okay, so the volume number is 1 here. How about the yellow one? Same, we select this one, gamma U, gamma V, and the right hand side is D minus, the left hand side is D plus. D minus is 0, so D plus is 1. So you get 1 here. Okay. Okay, so the result is the same as our experiment, right? We have determined the volume number by really tracing the curve space for every point. Right. So this theorem, even though it's very technical, but if you understand the picture here, the application of this theorem is very easy. You just identify which is D mass, which is D plus read domain, okay? And then you apply the result here. Okay, apply the result, again you have that. So anyway, you should be able to determine the index functions of with respect to any curve space. Okay, by these 2 theorems here. Okay, and I will give you the details of the proof in my lecture notes. So, but the point is to really understand the statement of the theorem. Okay? All right. So now we will state the Cauchy's integral formula first in a convex open set. Okay, so Cauchy's integral formula in a convex open set. All right, so gamma occurs the path omega is a convex open subset of C, and gamma is a closed path in omega. Okay, so R star, the range of this closed curve should be contained in this convex open subset. Okay? And the f is a function, a complex function in H omega. So which means that it's analytic on the complex open set. Okay. Now if Z is in the convex open subset, but Z is not on the closed path, then Then if we do the line integral gamma, all right? Okay, so the z, because z is not on the cross path, so the denominator never 0. So this is well defined. Okay, so if we integrate with the line integral of this integrand here, so this integrand is actually, all right, a ratio of that. So the line integral of this integrand over the cross path gamma divided by 2 pi I, then the value is actually equal to f of z. So it's f of z times the 1D number of z, all right, with respect to gamma. Okay. So this is very interesting. Okay, so we have this formula. So this analytic function multiplied with the 1 number of z can be expressed as a line integral. Okay, and the integrand here of this line integral is the ratio of the original function, right, to a linear term, okay, to a linear term here. If you like, maybe if you like here, if you use maybe you like okay, you use 0. So the integrand all right, so this is the integrand we have, okay, the integrand. Okay, so if the omega is the, so that must be convex open. So omega must be a convex open set. And okay, then we can consider arbitrary cross paths. Okay, so we can consider arbitrary cross paths here. And omega is convex. So convexity is very important. Open subset. Convex open subset. Okay. Another version is in a simply connect domain. So if we extend the convex open subset, because convex open subset is a special case of simply connected domain. So if the theorem for 3.1, so this is Cauchy's integral theorem formula. Okay, in a simply connected domain. Okay, so omega now is a simply connected domain. Okay, and the gamma is a simple closed path. Okay, a simple closed path. Right. In omega, and which moves counterclockwise. Right, so we give the orientation of this simple closed path. Right, so we have, and so if we are considering, so this is a simply connected domain, but it's not convex. You can see, right? This is simply connected domain. Right? Simply connected domain. And gamma is a simple cross path. So a simple cross path is here. There is no intersection with itself, right? And so the orientation is counterclockwise, right? So this is orientation here, gamma star. And so you can see here that the index with this, you see the index. So the index here x1. Okay, and this part is unbounded, right? Corresponding so the index here is 0. Okay. Right? So you heard that. Then under f, a complex function in the set of all holomorphic function on omega. Okay, and the Z a point in omega, but not in gamma star. So Z is a point. Z is a point here, either Z here or Z here. Okay, inside or outside the simple closed curve. So Z is a point, right? So there are two cases. Either Z is inside or Z is enclosed by the simple closed path, or Z is not enclosed by the simple closed curve, right? So there are only two situations. If z is inside, then the index is 1. But if z is outside, the index is 0. Okay? Then fz, fz0 here. I'm sorry. I use z0. Okay. So fz0 times the index of gamma z0 is equal to 1 over 2 pi I gamma f of psi minus z0. Okay. So we have the same formula. Okay, we have the same formula here. So this is the Cauchy's integral formula. And as you can see, if z0 is outside of the, so if z0 is not enclosed by the simple closed path, then this is 0. Okay, so the integral will be 0. Okay, but if z0 is enclosed by this one, so this is saying that the 2 pi I gamma equal to 0 if z0 is not enclosed by gamma. Okay, and it is equal to f of z0 if 0 is enclosed by gamma. Okay, so f0 can be evaluated by this line integral. Okay, of this integrand over the simple closed path gamma here. Okay. So for simply connected domain, the closed path we consider should be a simple one here. Okay. Any questions? Now we will answer our long-standing question. In chapter 13, when we consider analytic function, we say that if a complex function is analytic on an open subset omega, which means that this complex function is differentiable on the open subset omega, then its derivative is also analytic. Alright? So if the derivative exists, then the second derivative will exist, and then the third derivative, etc. Right? So we will answer this property in this section. Derivatives of analytic function Alright, so we will state immediately the main theorem of this section. Derivatives of an analytic function. Alright, so f is an analytic function on a simply connected domain D. Okay? And Z0 a point in the simply connected domain D. And the gamma is a simple closed path in D which moves counterclockwise, okay, and enclosed Z0. Okay, so the situation is here, and we have a simply connected domain. Right, so D, a simply connected domain. Excuse me. Right. And a point Z0, okay, in this simply connected domain. And we find a simple cross path. So the simple cross path may be here. Alright? So and the orientation is counterclockwise. So this is our orientation. So this is gamma star here. And it encloses Z0. Okay, so this is our situation. Is okay? Then the first derivative. We know f is an analytic function, right? And by the way, from Cauchy's integral formula, we know f0 is here, right? f0 can be equal to this one, right? Because z0 is enclosed by the simple cross path. So f0 is equal to this one. It's already here. Okay. But how about the f prime 0, the first derivative? And the first derivative is here. Very interesting. Again, the line integral over the simple cross path. And f of z and z minus z0 square and dz. Now we have square in the denominator. Okay. For fz itself, just the first power of the difference. But for the derivative, we have the second power. And we also have the second derivative. And the second derivative becomes to be the line integral over the simple cross path. By this time, the integrand would be z minus z0. And, oh, by the way, I forgot to put 2 factorial. And this is 3. The third power. in general, okay, we have the nth derivative at z0, and it's n factorial, and 2 pi I gamma fz, and here is z minus z0 with n plus 1's power, and dz. Right, so this answers our question that if f is analytical, which means that the f prime exists at every z0 in the simply connected domain D, then we can express the derivative at z0 as a line integral here. Okay. And in general, we have the nth derivative. Okay, we have nth derivative. And also, this nth derivative can be evaluated by a line integral. And the integrand here, right, is f of z divided by the n plus 1's power of the difference between z and z0. Okay. Well, the proof is a little bit long, takes 2 pages, a little more than 2 pages, but I have given you elementary proof, so it's not hard to understand the proof. Okay, but the main thing is that we can express the nth derivative by line integral. Okay, and the foundation is the Cauchy's integral formula here. Okay, as we see that the f of z, the value itself can be evaluated by this line integral. Okay, so that is the basic point we have. Okay, and from that, we are able to show that we have these formulas. Okay. Okay, so with this one, now we will state a theorem which answers our question in chapter 13. So let omega be an open set. Right? So omega be any open set, not necessarily only simply connected, just an absolute open set. If f is a homomorphic function on omega, then its first derivative is also in the homomorphic function, right? In the set of a homomorphic function on omega. So this just says that if f is analytical on omega, then its derivative is also analytical on omega. And the proof, okay, so we can use the previous theorem to prove this. Now we let z0 be a point in the open set, right? Now, since omega is open, there is an open disk D with the center Z0, the radius R. Alright, so with the center Z sub 0 and radius R 0. And this open disk contained in omega. Okay, so the situation is here is that in any probably here, okay, so omega and open set, okay, and then you pick up a point Z0, then you can select an open disk. Alright, so this is contained in omega. And we know the open disk is a convex open set. So it's simply connected domain. Okay? So that this is a simply connected domain. Thus, the open disk is simply connected domain in the compass plane C. And we know that Fz is analytic on D. Okay, because F is analytic on omega, so of course F is analytic on this is small set, right? This open disk. All right, now in this open disk, we select a simple closed. So we select, say, a circle here, and the positive oriented. Okay. Now, so the positively oriented circle gamma with the center Z0 and the radius half of gamma is a simple closed path, okay, in the simply connected domain, which moves counterclockwise and enclosed Z0. Okay? Alright, so we have everything needed in this theorem. Okay. So by theorem 14.4.1, the derivative of F prime exists. Okay, at Z0. Okay, second derivative exists, right? This is the derivative of f prime at z0. Right, and since z0 is arbitrary, it's an arbitrary point in omega. So f prime is in h omega. Okay. So any questions? The following theorem is a very good estimate of the nth derivative of an analytic function. Okay, so it's quite useful. So let me see. We call it as the Cauchy's inequality. Okay, so if f is in here, right, DAR, which is an open disk with center A and radius big R. Okay, so F is analytic on this open disk, and suppose that this upper bounded for all Z in this open disk. Okay. Then, right, so we know that the function value has magnitude upper bounded by m for all Z in the open disk. Then we can estimate the size of the nth derivative at A. Okay? At A. Now, so this will be upper bounded by n factorial times m divided by n to the power of r for n equal to every positive integral. So this is a very good estimate for this one. Okay, for the nth derivative. Okay. And a very interesting theorem will be stated here. We call Liouville's theorem, which quite often to identify constant function. So this theorem says that every bounded entire function is a constant function. Right? Entire function is analytic function on the whole complex plane. For example, the exponential function, right? Exponential function is an entire function. The other is the sine function or cosine function. They are also entire functions, right? And hypercosine, hypersine, they are all entire functions. But logarithm is not the entire function. Okay. Now, if an entire function is bounded, bounded means that the function value has magnitude upper bounded by some specific numbers called m. So if you have a bounded entire function, then this function must be a constant function, which means that if you have a non-constant entire function, then this entire function must be unbounded. Okay, must be unbounded. It's called Liouville theorem. All right, and the last one. So the following theorem is a converse of Cauchy's integral theorem. Okay, it's called the Morera theorem. So let me state it. Okay, so if fz is a continuous complex function on an open set omega such that if we integrate this continuous complex function over the boundary of a triangle, you know, the boundary of a triangle must be across the path, okay? So if such that this is true, this is equal to 0. So if this integral is 0 for every closed triangle delta contained in the open set, then this function must be holomorphic on omega. Okay. So Morera's theorem is also a good theorem to identify holomorphic functions. Okay. So if we can show that the function is continuous itself, and to show that for every closed triangle contained in the open set, such that if you integrate the function f over the boundary of the triangle, the line integral is 0. If this is true, then you know the function f is analytic. Okay. Okay. So this is also a very useful theorem there. Okay. All right. So so I have completed the chapter 14. Okay. And I will send you my lecture notes because I didn't give you the proof. Okay. And which will be in my lecture notes. Okay. Any questions? Okay. And also, I will give you lecture note of 15 together because I ask you to self-study the first section about the convergence of power series. Okay, I believe that you have learned this subject in calculus, so I think you will have ability to preview the subject of the first section. Okay. Right. So I'll stop here, and I'll see you next Tuesday.